Hello, and welcome to Lesson 7 of this Introduction to Calculus with Wolfram U. Our topic for today is derivatives and rates of change. So let's begin with a brief overview of today's lesson. So at the start, we said that calculus is the science of change. So the primary goal of calculus is to study change. Now, there's one way to study change, and that's to use functions. So functions tell us how one quantity changes with respect to other quantities. So for example, here's a function which relates x to f of x or y, and that's the plot of the function. So that tells you how y changes with respect to x. But of course, we need more than that. Often we need to know how the function changes from point to point. So we need the rate of change, so to speak. So if you have a straight line, that's simple. You simply find the slope. So here's a straight line. The slope is 3, and that's a very nice measure of the rate of change of that function. So in this lesson, we'll show you how to do that for more general functions. In other words, we'll try and generalize the idea of slope using what are known as derivatives. So that's the theme for today, derivatives and rates of change. So let's begin with the notion of a derivative. So the derivative is a special kind of limit, and that limit, roughly speaking, is linked to the tangent to a curve. I haven't told exactly how, but we'll see that later. So for example, if you have a straight line, the simplest kind of curve, then the slope of the straight line is rise over run. So that's difference in y or difference in x. And in the f notation, that's f of x minus f of a over x minus a. So the question is that good enough for a general function f? And the answer is no. This only gives us the slope of the secant line for an arbitrary function f. So let's see that here's a function f of x equal to 1 over x, a very simple function, and let's take 2 points on it, 1/2 and 2, and 3 and 1/3, and work out the slope of the secant line joining those 2 points. That's negative 2/3. Now if you draw the graph of the function and that secant line, you see that it's not quite what we need. It's just a little too far off to be useful. So what's missing over here is that the 2 points need to be really close by, and so really what we need is the notion of limits that we studied earlier on. So to find the tangent line to a curve at a point, you really need to take the limit of secant lines. So to be more precise, you need to find the difference in f between x and a, or the difference in x itself, and then take the limit as x approaches the given point a. And this is what will give you the slope of the tangent line that goes through the required point a comma f of a. So here's an example to show you that. You have a secant line over here, and then as you let the points come closer and closer, you will then get the tangent line. So it's only in the limit that you actually get the tangent line starting from a secant line. Okay, so as an example of a tangent line, let's take the curve f of x equal to x cubed, and here's the slope of the secant line through the point 1, 1 in the limit, and that's the slope of the tangent. So if the slope is 3, then the equation is y minus y1 equal to slope times x minus x1. And if you plot that, you surely do get the tangent line to the curve x cubed at this point 1, 1. So just to summarize, given a point on a curve, what you do is you first work out the limit of this quotient over here. You get the slope. That slope can be used to find the equation of the line, and that line is then the tangent line. So it's slope times x minus x1 plus y1 in this plot over here. Okay, in practice, of course, we use something called the difference quotient to find derivatives. So here's the difference quotient. What it says, you go on the limit as this number h approaches 0 of the difference between f at a nearby point and at the given point over h. So it's still a slope, but it's a slope in a slightly different form. So as an example, suppose f of x is 1 over x. You work out the slope over here, and you get negative 1. Now, once you've got the slope, what you can do is you can plug in and find the equation of the tangent line, and here you are. That is the correct tangent line at the point. Okay, now a couple of places where you might find this notion. So first of all, the idea of velocity. So the instantaneous velocity of a position function is given by the slope of the tangent line to the position curve. So if a particle is changing position and you want to find the speed or the velocity at a particular time, then all you do is you work out the tangent line to the curve at that point. So for example, suppose that the position is this very simple function, s of t equal to 5 times t. You work out the velocity by doing the difference quotient calculation we did early on, and then you find out that in fact the position is in this case a linear function while the velocity is constant, which of course you could have guessed from earlier work in your class on physics or other subjects. So this is the notion of velocity as the derivative of position. Okay, so a slightly harder problem. So suppose a ball is dropped from a building 100 meters above the ground. Now you want to find the velocity of the ball after 2 seconds, let's say, and you want to find out how fast it is going when the ball hits the ground. So there are two problems over here. You want to find what the velocity is after 2 seconds, and you want to find out how fast it is going, the ball is going when it hits the ground. Now you can work out the equation of motion as 100, the initial height, minus 4.9 t square. That comes from the acceleration due to gravity. And then what you can do is you can work out the speed at time t equal 2 by using the difference quotient calculation. Now the question is, why is it negative? Well, it's negative because the ball is going down. So if you plot the position and the tangent equation we saw just now, that's the velocity over here. Okay, the question now is, what happens when the ball hits the ground? Well, when the ball hits the ground, the displacement is 0. So you solve that equation which just says that the displacement is 0 when the time is about 4.517. And you can plug in into the derivative, the speed, and you get back negative 44.2719. So that's the way to find out what happens to the ball when it hits the ground, what the speed is. Okay, now the question is, what is the slope of the tangent line at a point? Well, it is the derivative at that point. So when people say derivative at a point, what they really mean is the slope of tangent line and vice versa. Now we have a shorthand for it. We use the notation f prime x over there. So if you say f of x equal to x cubed, then in the Wolfram language, f prime at 1 is the derivative at x equal to 1. So the derivative of x cubed at 1, 1 is 3. And you can plot that and check that it in fact is the correct answer. A couple of more concepts over here. So first of all, we have the notion of a tangent line to a more general curve, like over here you got the tangent line to a parabola, and you want to work out the tangent equation for that parabola. So what you do is you set up an equation which is y equal to slope, the derivative, times x minus x1 plus y1, and you work it out, and then you get actually the required plot of the parabola with the tangent line at x equal to 2. Now, sometimes people talk about the average rate of change. So suppose you've got a function y of x. And let's say x changes from x1 to x2. Naturally, y changes from some y1 to y2. So the increment over here means the change in x, and the increment over there means the change in y. So you've got delta x and delta y telling you what the change in x and the change in y are. And their ratio is what's called the average rate of change of y with respect to x as you go from x1 to x2. And this average rate of change is exactly the slope of the secant line joining the 2 points. So for example, if you want to find the average rate of change over this interval, you simply find the difference in the function values, divide by difference in x values, and you get back the average rate, and here is a plot of the secant line along with the original curve. Okay, so as the secant line goes closer to the point, then of course you get the instantaneous rate of change. So the instantaneous rate of change is the change that you get when delta x, the change in x, goes to 0. And that is exactly the slope of the tangent line at that point. So in our case, if you take a limit in the earlier calculation, then you get back the tangent line at the point. So the instantaneous rate of change is exactly the derivative of y at x. And finally, an example involving tables. So here is the table showing the US national debt in billions between 1980 and 2015 measured at 5-year intervals. So here's a plot. It's clearly going up. The question is, can you estimate the instantaneous rate of change at the year 2010? So the first step, what you do is you make a piecewise function from it, because that lets you build the function starting from the data. Now you want to find derivative, so you set up the quotient like you did early on. You want to find it 2010, so that's where that comes from. And then you can kind of interpolate. In other words, you find an average of the values between 2005 and 2015, and that, roughly speaking, is the instant rate of change at 2010. So roughly speaking, the rate of increase of debt is about $1.1 trillion in the year 2010. Okay, so that brings me to the end of today's lesson, and the point is that the derivative of a function is simply the slope of a function at that point. You can think of this derivative as being the limit of the slopes of secant lines. So if you start a secant line and take a limit, then you get the derivative of the tangent line. Now, the derivative idea is very useful in lots of places, like we saw for speed and that kind of thing in physics, and also for calculating, let's say, debt in economics. Often, the only data you have is a table of values, in which case you can approximate the derivative. And so the idea is that starting from a table of values, you can find the approximate value, but of course you cannot calculate the exact value of derivative. So that's the idea for today, the idea of a derivative and the notion of rate of change. And in the next lesson, we'll talk about the derivative itself as being a function, just like the function that you start with. So I'll stop over here. Do go over today's lesson, try the exercises, and you should be in good shape for the next lesson, which is lesson number 8. Thank you.